About 100 years ago, there was a group of scientists, including Max Planck and Albert Einstein, that proposed that maybe energy has particle-like characteristics as well as wave-like characteristics. So as part of this proposal, Einstein developed the idea of a photon, which is an energy packet. So if you think about a package or any kind of packet, or even if you're going out and you're picking up food, right? Sometimes your food comes in a small bag or a medium bag or a large bag. Boxes, right? You get a small box or a large box. They come in all different sizes. So our photons, these energy packets, also come in all different sizes. However, sometimes you're just out of luck. Like sometimes you have a small bag and a medium bag, but there's nothing in between the small and the medium. And that's what it means when they talk about these photons as being discrete or specific. And this is in contrast to what we would expect if they were waves, if they were just only waves. Because if we think about a wave is going to cover every single possibility. So you're going to have small, you're going to have something a little bit bigger than small and a little bit bigger there. Every single value is covered with a wave, whereas with a particle or a photon, we have specific values, non-continuous values. Additionally, photons, even though they're packets, and I'm comparing them to boxes and bags here, they're still just energy, and energy doesn't have mass. So photons can't rightfully be classified as matter. All right, so the set of problems that we're going to work on in this video deal with Planck's equation. So Planck was one of the first scientists to extrapolate the relationship between the energy of a photon and the frequency of light. And so the constant that relates those two variables is named after him. So we have H, which is Planck's constant. You'll notice on my units here, I have the photon in a blue bubble, a blue cloud on the bottom. We don't always need to divide by photons. However, if you're doing a problem and it says calculate the number of photons or calculate the energy of the photon, then it really helps to divide Planck's constant by photons. However, at a minimum, the units will be joules times seconds. Then you have the E, the big E, which I briefly mentioned. This stands for energy. So we expect units of joules for that. And then the nu, you're familiar with that from the previous lesson. That's going to be our frequency. And that has units of 1/seconds, or hertz. There's another version of Planck's equation, and you can totally derive it because we know that the speed of light is equal to wavelength times frequency. If we solve for frequency, we get c divided by wavelength equals frequency. And we can just take this relationship and plug it in for frequency. So then we get a second version of the equation that I find pretty handy. E equals hc divided by lambda. So Planck's constant times the speed of light divided by lambda. Which one do I use? Well, it just depends on what the problem gave me. If the problem gave me frequency, I use this one. If the problem gave me wavelength, then I use that one. Alrighty, so in this first problem, dealing with Planck's equation, we know that we need to use Planck's equation because they're talking about photons. And they gave us a wavelength, so I'm going to use the version E equals hc divided by lambda. Pretty much have all that information. This is a constant that I could look up. This is another constant. And then the wavelength, the 525 nanometers, was provided. That's going to allow me to solve for the energy of one photon. So energy per one photon. Now, the photons are particles, but they're also super, super small. So if you have a 100-watt light bulb and they're asking you how many photons are emitted per second, we expect there to be a lot of photons. And there's nothing about seconds in Planck's equation, but I'm thinking, and this is where these problems get really tricky because every single one requires like a creative approach. I'm thinking maybe I can use this value as some kind of conversion factor of sorts. So maybe I could use something like 100 joules per 1 second, and then they want photons per second for the final units. And I'm almost seeing here that if I flip this, then the joules from this one will cancel out those joules, and then I'm gonna have photons per second. But let's see if that'll work out. So first step, we're never gonna keep the wavelength in nanometers. So I'm gonna convert nanometers to just meters. So I'll divide by 1 times 10 to the 9. And that gave me 5.25 times 10 to the negative 7 meters. And so I have energy per photon, put a subscript there to remind myself of that. Energy of 1 photon equals Planck's constant, so 6.626 times 10 to the negative 34 joules times seconds divided by photon times the speed of light, so 2.998 times 10 to the 8 meters per second. Do a big set of parentheses in the numerator. When you're plugging this into your calculator, if you're going to do it all in one step, put a big set of parentheses. Divided by the wavelength, so the 5.25 times 10 to the negative 7 meters. Let's look at the units and then we'll get the answer here. So meters will cancel meters, and then we have seconds in the numerator here, and there's seconds in the denominator here. That will cancel. And then our units at this point will be joules per photon. When I plugged that in, I got a value of 3.7 838 times 10 to the negative 19 joules per photon. So there's going to be this relationship that we'll see in a lot of these problems. The photon is just a little packet. So if we know the total energy, and we divide by the energy of just 1 photon, then we can get information about the number of photons. And students are often bothered by that. They're like, well, how do we come up with that relationship? The way that helped me understand it when I was a student, I used to think about the Halloween candy that comes in the fun size. So if you're gonna go buy some Halloween candy and you know the mass of the bag, the whole bag, and then you know the mass of one of those little candy bars, mass of one like fun size Snickers or something like that. And then if you think about that, we know the total mass and we divide by the mass of one candy, then that's going to give us the number of candies in the bag. So it's the same idea here, where the photons are like our little fun size Snickers. So we got a total energy, which is defined by the wattage of the light bulb. So we're going to do 100 joules per second. Our equation says to divide. Remember, when you're dividing by a fraction, you take the reciprocal. So I'm going to divide by this value over here. So I'm going to divide by the fact that one photon has 3.7838 times 10 to the negative 19 joules of energy associated with it. Joules, cancel joules, and then I'm left with photons per second, which is the units that we wanted. And I got 2.64 times 10 to the 20 photons per second. My mind is always blown by this value because a 100-watt light bulb is pretty common. And this is how many little energy packets are potentially hitting us per second. Not that I'm concerned about it. The energy, the wavelength isn't gonna damage us. But the other thing, when you're checking these, you never want to get a fraction of a photon. So if I had set this up incorrectly and I got 2.64 times 10 to the negative 20 photons, that wouldn't make any sense because we can't subdivide a photon. So make sure you always have a positive number, and usually it's going to be pretty big because the photons are super small. So another problem that uses Planck's equation, we know that we need Planck's equation because they're asking us about photons, and that's a big tip-off. We are given the wavelength in nanometers, so let's take care of that first. We need to convert it to just regular meters. So 532 nanometers. So when I did that conversion, I got a value of 5.32 times 10 to the negative 7 meters. Additionally, we have this 3.85 millijoules value, and that represents the total energy. However, the milli is a little bit problematic, so I'm going to convert it over to joules before I jump into the problem itself. So there's 1,000 millijoules in 1 joule, just like there's 1,000 millimeters in 1 meter. And that leaves me with 3.85 times 10 to the negative 3rd joules. Now I'm going to use Planck's equation to solve for the energy of the photon. So I'll use the version with wavelength. So h times c divided by lambda. We have 6.626 times 10 to the negative 34 joules times seconds divided by photons times the speed of light, the 2.998 times 10 to the 8th meters per second, divided by lambda, the wavelength, so 5.32 times 10 to the negative 7 meters. As always, I'm going to look how my units are canceling. So meters with meters, seconds with seconds, which leaves me with this joules per photon unit. So the energy associated with 1 photon, I got a value of 3.73398 times 10 to the negative 19 joules per photon. At this point, since we know the total energy and the energy of 1 photon, we can divide those two values to determine the number of photons. So I'm using this relationship. Energy total divided by energy of the photon equals the number of photons. So the total energy, we converted it over to joules a little bit earlier. So 3.85 times 10 to the negative third joules divided by 3.73398 times 10 to the negative 19 joules per photon. Joules will cancel joules. When you have a double fraction and something's in the bottom of the double fraction, it flips up to the top. So I wound up getting 1.03 times 10 to the 16 photons as my final answer.
Can you test me on my Spanish vocabulary?